lesson. In our lesson today, we're going to look at a revision question in physics, which is coming from Hooke's law. And the question reads, a learner carried out a Hooke's law experiment and obtained the following results. So we have got table C 2.1 there, the mass in kg, length of loaded spring in centimeters, applied forces in Newton, then the extension in millimeters. So the question says, copy and complete table C 2.1 by finding values of applied newtons and extension in millimeters produced. Okay, so if you look at this one, we need to know how to calculate these things. Okay, so we need to derive a formula for applied force. Now kindly take note that applied force will be mass multiplied by the gravity here, which is 10 Newton slash kg. Okay, so if you look at the first one there, the mass is 0 multiplied by 10, the applied force will be 0. The first one, then the second one 0.02 multiplied by 10, the answer there will be 0.2, and the next one 0.04 multiplied by 10, the answer will be 0.4. Next one 0.06 multiplied by 10, the answer there will be 0.6. Next one 0.08 multiplied by 10, the answer there will be 0.8. Then 0.10 multiplied by 10, the answer will be 1.0. Take note, when you are finding the applied force, your mass is supposed to be in kilograms. So if it's in grams, you have to convert it to kilograms. Okay, then we go to extension. What is this so-called extension? Okay, extension basically, okay, this is the increase. Extension is an increase, okay, in length of a spring when it is loaded. It is loaded. Okay, so therefore, for us to find the extension, meaning you need to find the difference between the length of a spring when it has got a load minus the length of a spring without a load. Okay, so if you look at this one, we are told that without a load, the length of a spring is what? Is 11. Okay, so if you are to put a load of 0.2 newtons, there will be an extension, okay, of this spring to 12.1. So the difference between 12.1 and 11, that will be 1.1 centimeters. Therefore, we are told that the extension is in millimeters, so you multiply it by 10, and that's going to give us 11. In the first box there is no extension, it's 0. Now, how are we finding this 11? Take note that 1 centimeter is equal to 10 what? Millimeters. So this is a very important point to take note of. Okay, so second one, when there's a load of 0.4, okay, the length increases to about 13.2. So meaning what will be our extension there? 13.2 here minus 11, that's going to give us 2.2. Then if you get your 2.2 there, that 2.2, you are supposed to multiply it by 10 so that you get the answer in millimeters, and that's going to give us 22 millimeters. Next also we have the 14.3 there, okay, minus the 11, it's going to give us a 3.3. You multiply by 10, it's going to give us a 33 what? Millimeters. The next one, when the load is 0.8, the spring will stretch to 15.4. Then you subtract with the 11, you are going to have the 4.4. When you multiply by 10, it's going to give you 44 what? Millimeters. Okay, the next one, 16.5, okay, minus the 11, you are going to get the 5.5 multiplied by 10, that's going to give us 55 millimeters. Okay, so you'd have completed your work, okay, where you have your applied force and your extension. So we go to question B. What is question B saying? Says plot the graph of applied force. So the one that they start with becomes the y-axis. So meaning the applied force there will be the y-axis. Then the against is the x-axis. So you are told to plot the graph of applied force against the extension in what? In millimeters. So when you are plotting a graph, there are things that we need to take note. Number one, your graph should have a title. So in this case, we're going to have applied force against extension. Okay, then also we need to come up with a scale, because in physics they don't give us a scale. It is up to us to come up with a scale that's favorable, and also seeing to it that at least our graph occupies more than half of the graph paper. Okay, then also apart from that, we're supposed to know what each small box is representing, both on the x-axis and also on the y-axis. So come up with a graph that looks like this, where we have got a title there, applied force extension graph. We've got the y-axis there, and the x-axis there, you've got the extension, and we also have got the applied force in Newton there. Okay, so the first thing that we'll start doing now is to plot those points on the graph paper. So just like what we have said, that the applied force is representing the y-axis, okay, then the extension is representing the x-axis. So you start with a 0,0 there, okay, 0,0, it is there at the origin. Next point, 11,0.2, that is here. Next point, 20,0.4, that is there. Next point, okay, so a second point there was 22,0.4. The next point, we're going to have 33,0.6, 33,0.6, somewhere there. Next point, 44, okay, 0.8, should be somewhere there. Then the last point, it's 55,1.0. That should be there. So once you are done with the plotting, you are going to join this, okay, with a smooth straight line. Okay, which looks like that. Okay, so as you can see in this graph, as the the applied force is increasing, the extension is also what? Increasing. So in this case, we can be able to summarize by saying this graph basically it obeys the Hooke's law. Now, what does Hooke's law state? So we're going to say that Hooke's law states that the extension of a loaded spring is directly proportional to the applied force. Meaning as the extension is increasing, also the applied force is what? Is increasing. Let's look at the next question. We are told from the graph, determine the spring constant. Meaning we should find the constant of this spring. So the constant of the spring, or the spring constant, can be calculated by the change in y, over the change in what? In x. So in this case, we shall say the change in y over the change in x. So what do we do there? This spring constant, it is what we describe as a gradient. Spring constant, or the slope. So change in y over the change in x. So you pick any points. Let's assume that we pick a point here, which is 11,0.2. Then here again, can pick a point there, which is 22,0.4. So after we do that, we're going to label here x1, y1, then x2 there, y2. So what is our y2? Our y2 is 0.4 minus, what is our y1? Our y1 is going to be 0.2. 0.2 divide x2, got a 22 there, minus x1, we got 11 there. So therefore, when you subtract 0.4 minus 0.2 to give us 0.2 divide 11 there. So when you divide the 0.2 divide 11, it's going to give us 0.018, which when you round it off, it's going to be 0.002 there as the slope. So we are told that this slope, it is constant. We continue. D, number 1. Did the spring reach its elastic limit? Did the spring reach its elastic limit? Okay, the answer is no. Okay, the reason why the spring did not reach the elastic limit is that the extension of a loaded spring was direct proportional to the force applied. Okay, meaning this line, this graph that we have drawn was straight. There is no point where the graph had to bend. Okay, so reason, okay, the extension of a loaded spring okay is directly proportional to the applied what? To the applied force. So hence the graph did not bend. The graph did not bend. Okay. We have come to the end of today's lesson. We'll be able to meet next time, even as we'll be looking at other components